like good doors and windows in their homes. To make the complementary other half of a mortise and tenon joint, your tenon, I'm standing here next to a tenoning machine. This machine was also made by the same company that made the mortiser, H.B. Smith, and this has a patent date of 1866. Smith was the first person to make an all iron and steel tenoning machine. Other people made tenoning machines that weren't quite as good as this one, that might have had a wooden frame. Now basically what this machine is going to do is it's going to simultaneously cut both sides of this tenon at the same time as I push this sliding table under the cutter head. And I'll go through a kind of a slow motion on this so you can see exactly what's happening. Now we'll demonstrate exactly how this machine works, and we'll run it kind of slow motion once again. We'll tension our belt here. Now, as I turn this belt, you will see basically we have two cutting heads on horizontal shafts, or what they're referred to as arbors. These cutting heads have cutters on the end, which you might be able to see here have a radius cut on them. And believe it or not, that radius knife can cut a true and flat surface because it's hitting the surface at a skew angle. And you can regulate the positioning of these two cutter heads by sticking a crank and turning either the inner screw or the outer screw. And one of Mr. Smith's patented features was a lever here that you can push, and when you turn one crank, you'll move the two of them simultaneously up and down as a pair. Now, this machine needs to run at that very high speed, and if you remember, our line shaft is going about 250 RPM, so we need to basically step up from 250 up to 3600. So we go through several speed changes. From the main line shaft up above, we'll go from a large pulley down to a smaller pulley on our counter shaft. And then you might notice here that this one pulley is made out of wood. Now oftentimes wood pulleys were popular on counter shafts and line shafts because, one, they were light in weight, they were cheaper than a cast iron pulley, and the other advantage was they could be made in two halves. I have one here on the floor, which I'll pick up, and you can see your pulleys would split so that you could position a pulley anywhere you wanted, and you didn't have to take the shaft down to slide the pulley on. So that was a great advantage. Now, when I pull on the belt here, simulating the machine running, you will see that the power is transmitted from the counter shaft once again from a larger diameter pulley. This pulley is approximately about 16, 17 inches in diameter. We're going down to about an 8-inch pulley. So we're basically doubling the speed of this lower counter shaft. And then if you follow over, this counter shaft is running this pulley here. And once again, we're back up to about a 15-inch, 16-inch diameter pulley. And then the pulleys on the cutting shafts, they're about 4 inches in diameter. So there we go from 16 to 4. You basically have a 4-to-1 speed increase. And this belt kind of snakes around through these pulleys, and by it doing that, it rotates the two cutter heads in opposite directions as the wood will get pushed under. And this pulley right here is basically just an idler that tensions it has a weight hanging here, and that tensions the belt to keep the belt at the proper tension. And it also allows for these heads to be moved up and down, and then this will automatically compensate for the repositioning. Now, if you notice this machine, the frame of this machine is a whole series of Gothic arches. Early woodworking machines and also metalworking machines to a certain extent tended to be rather decorative. And a lot of times they followed popular architectural themes of the day. And in the 1860s, Gothic revival was popular. So basically they're kind of copying that a little bit. And also you'll notice all these little brackets and curlicues on the frame of the machine here. By the early 1880s, it was more strictly a kind of form-following function, and they stopped making machines decorative. Now we'll turn the machine on and we'll give you a demonstration of the machine running under power. We'll shift the belt over to the driven pulley here. Actually, you can hear the steam engine, the governor kicked in and increased the steam to speed it up. Now we'll pull this out and we'll take our blank of wood, put it on the table. As you can see, in less than a minute, I cut 6 joints. And it doesn't take a very skilled person to operate a machine like this. So if these were cut by hand, it would probably take a good 45 minutes. And once again, machines like this allowed doors and windows and cabinets to be made in factories for the first time, where previously they would be made by individual craftsmen. The next machine I'd like to demonstrate is called a shaper, or as our British friends refer to it, is a spindle molder. This machine was made by the S.J. Scheimer Company in Milton, Pennsylvania in the mid-1870s. On a wood shaper, you have essentially a vertical shaft this time, which has a cutter head mount on it. And these machines were typically used for cutting molding profiles, for doors, windows, and for short-run moldings. Now, a machine like this presents a interesting power transmission problem for the 19th century, in that all your line shafts in factories ran horizontal in the ceiling. So essentially what you have to do is you have to transmit your power and somehow convert it into a vertical rotating motion. The way this is done is the power is transmitted down through this belt and it rotates this horizontal counter shaft. If you look at the right side of the counter shaft, you'll notice what kind of looks like a bevel gear, but it's smooth, it doesn't have any teeth. What this is made out of is referred to as a paper pulley. It's made up of about 300 layers of tarred paper. And to turn the machine on, we kick a lever, and what that does is it shifts this paper pulley against a smooth-sided cast iron pulley, and that transmits the power to this vertical shaft in the rear. Now that has, once again, about a 16-inch diameter pulley. We're going down to about a 2.5 to 3-inch diameter pulley this time. Basically, we're increasing the line shaft speed of 250 up to about 5,000 on the spindle. Now, when I kick this over, this will activate the machine. Well, wait a minute, I forgot to move the line shaft. I mean the shifter lever first. Now, as you can see, we have our under machine counter shaft rotating. And when I kick this over, it will start the spindle. Basically, we cut a profile that's used in window sash construction. This would be towards the room, and then your pane of glass would fit in this groove, which is called a rabbet. Woodworking shops and factories in general basically started to electrify around 1910. And that's when the shops that could afford it would purchase new machines that were powered by individual electric motors. However, oftentimes your factory didn't trade in its steam engine. They basically would trade in their steam engine, which ran the line shafts, for a newer steam engine, which would run a generator set to generate electricity. This was necessary because the power grid back in those days oftentimes didn't have enough capacity to supply a factory with the amount of power it needed. So the factory would essentially generate its own electricity using a steam generator set. Now in Allentown, Pennsylvania, there was a company called the Bueller Furniture Company, and what they did was they electrified in 1928, and they purchased a Harrisburg Uniflow generator set, and they generated their own electricity. Basically, the line shaft shop era was over by the mid to late 1930s. As you might have noticed, in a shop like this, there's a lot of safety and health issues with moving belts and gears and shafts and things like that. When line shaft shops were converted over to machines powered by direct drive motors with guards and things like that, the workshop became a lot safer place. There were a few holdouts, however, but by the mid-1950s, the line shaft shop era was over. The 19th century marked a momentous transition in the history of woodworking, from the age of hand tools to the age of machinery. This transition was brought about by the rapidly growing U.S. population and its ever-increasing demand for homes, furniture, and other wooden objects. Raw materials were not the problem. Unlike Europe, America was blessed with bountiful forests. There simply were not enough skilled craftsmen to keep up with the demand for wood products. The first generation of woodworking machines were made possible by advances in precision metalworking and the sheer ingenuity of Yankee inventors. The period between 1835 and 1875 witnessed the development of most of the basic woodworking machines used today, as well as some wonderfully ingenious devices dedicated to highly specialized tasks. The earliest machines were located in factories along rivers and streams and were driven by line shafts powered by water wheels. But for communities lacking water power, steam power soon proved to be the answer. The number of steam-powered wood shops grew rapidly during the mid-1800s, especially after the Civil War. With post-Civil War economic growth, even small towns had at least one steam-powered planing mill. During this era, factories first started mass-producing stock windows and doors to be sold through catalogs. Cast iron was king as America rose to international preeminence in woodworking machine technology and production. Many machines of this period were exuberantly embellished with fanciful castings and painted decoration, presumably to celebrate these grand inventions that worked faster, cheaper, and with greater accuracy than the most experienced craftsmen. By the late 1880s, however, decoration gave way to a more utilitarian design sensibility that continued into the 20th century. In the early 1900s, the more innovative machinery manufacturers began to offer machines driven by electric motors as an alternative to their line shaft driven models. Large numbers of factories with sufficient capitalization replaced all their machinery during the 1920s, making the transition from line shaft power to electric motors. Because the local power grid often did not have sufficient capacity, it was not uncommon for factories to generate electricity with their own steam-powered generator set. Additionally, electric motors necessitated improvements in machine bearings, and this era marked the transition from poured Babbitt bearings to ball and roller bearings. A great number of old-time regional machine manufacturers went out of business during the Depression because they could not afford to redesign their entire product line. Thus, the sun gradually set on the steam-powered line shaft-driven shop, and by the 1950s, the last holdouts ceased to exist.